Next, we're going to talk about a system from Amazon called DSSTNE. That stands for Deep Scalable Sparse Tensor Neural Engine. Back when I worked at Amazon's personalization team, our algorithms and systems were some of the most closely guarded secrets in the company. But in 2016, they open-sourced DSSTNE and published an article on exactly how to use it to produce recommendations at Amazon scale. DSSTNE makes it possible to set up deep neural networks using sparse data, like the ratings data we have when training recommender systems, without writing a single line of code. All you have to do is convert your training data into the format DSSTNE expects, write a short configuration file that defines the topology of the neural network you want and how it's optimized, and it does the rest. DSSTNE also runs on a GPU and can process massive amounts of data very quickly. If your PC has multiple GPUs, it can even distribute the load across them and compute recommendations in parallel. And if you need to scale up even further, you can integrate DSSTNE with Apache Spark to run it across a larger cluster. Let's start by digging into an example of using DSSTNE on a single machine, and then we'll talk about how to scale it up to a cluster. Just to make it hit home, here is the entirety of the config file that trains a 3-layer neural network on the Movie Lens dataset, and it produces some really amazing results. Amazon has really made it as simple as it can get. Let's walk through this a bit. We start off with some information about the neural network at a high level. We are creating a feed-forward autoencoder. Specifically, it's something called a sparse autoencoder. In this context, sparsity refers to placing constraints on the hidden layer to force them to find interesting patterns, even if there are a large number of hidden nodes. The values under sparseness penalty define those constraints. The details of what these values represent would require you to find the lecture notes from Andrew Ng's CS294A course at Stanford about sparse autoencoders, but those are available online. However, usually the defaults are a decent starting place. Next, we specify that we don't want to bother shuffling the indices, but we are applying denoising, which will randomly flip one inputs to 0 for the probability specified, in this case 20%. This forces the hidden layer to discover more robust features, instead of just converging on one-to-one relationships, by making it reconstruct the input from a corrupted version of it. It's kind of weird, but we talked about this a bit in our deep learning tutorial. You get better results by forcing your neural network to work harder, be it from hiding information from it, or in this case, straight up messing with its inputs on each iteration during training. Next, we define the parameters for our loss function. These are actually a little bit different from the defaults, which are 0.9, 0.1, 1.0, and 1.0, so I think some hyperparameter tuning has already been done for this example. It's not far off, so the default values are probably still a good starting place. Finally, we get to the meat of it, the layers, where we define the layers of our neural network. Ours defines 3 layers. The first is the input layer. Note that we specify it as sparse. This is what makes DSSTNE special. It is built for the case where most of the input data is missing. The input case here is a lot like the RBM example we looked at earlier. For each user we train our network with, we have an input node for each possible item, which is set to 1 if the user rated that item, but the vast majority of items were not rated by any given user. This means our input data is very sparse, and by specifying this layer as sparse, DSSTNE knows this and can deal with it efficiently. We set n to auto, meaning it will set up as many input nodes as we have inputs in the data file, and that data file is given by the file named gl_input. Our second layer is the hidden layer, specified as such. It is fully connected with 128 nodes and a sigmoid activation function. It too is sparse. And finally, we have our output layer. We give it the answers for training purposes in the GL output file and set n to auto so it can adapt to the structure of the features in GL output we are trying to predict. It too has a sigmoid activation function, which is what we generally use for binary output. To take a step back, you may have noticed that this architecture seems to assume binary inputs and outputs, but the Movie Lens rating data exists on a 1:5 scale. It turns out that in this example, they discard the actual rating values themselves. They take any rating as an implicit binary indication of interest in the movie, and it works surprisingly well. However, you could do the same trick we did with RBMs and model each rating value as an individual binary classification to get finer-grained results and predictions. Let me show you this in action.